Yeah, good morning, everybody. It's very nice to be here. Thanks very much for inviting me, for having me here. Yeah, I want to talk about three-body recombination. So you have three atoms, and then they form, in three-body recombination, they form a molecule. But in fact, there can be many states that can be formed. And for example, here there can be a different molecular state, which has a red color here. And we want to investigate a little bit methods to control which way the reaction goes. Yeah? And will the reaction produce rather a blue molecule or a red molecule? And with this, we have developed some tools, and we call them like a beam splitter in some sense, where we can redirect the reaction flux that's occurring so that it goes either this way or this way. And the whole thing should be coherent. And in some sense, it's really like what you do when you have an optical beam splitter. You have a laser beam, and you send it onto a beam splitter, and it coherently gets split up into one path or the other path. Now here we have a beam splitter where we can control how much power goes one direction or the other direction. So that's the idea. And the work has been done in a fruitful collaboration for years. We've been working together. Here on the left-hand side, we have our theory colleagues. So Paul is here, and Jose is here, yeah. And Jose has been taking care of a postdoc in my group, Jinglun Li, who is a theorist. And so over thousands of kilometers, they've been working together. And so Jinglun is now in Austria at ISTA. Then we have this nice collaboration with Eberhard Thiemann, who is a spectroscopist. And then here's our experimental group in Ulm. So experiments were really carried out by Dominik Dora and Shinsuke Hase. And Shinsuke now is an associate professor in Osaka. So there are two beam splitters that I want to introduce to you. The first beam splitter is based on a Feschbach resonance. And the second one is based on an avoided crossing of two molecular levels. And of course, I have to explain in the following, how they work. But first, a little bit of introduction. Yeah? So we have this, these three rubidium atoms in our case, and we can prepare their quantum states, the internal states. They collide at ultra cold temperatures, so they collide in an S wave. And then, of course, three-body recombination takes place. This is a coherent quantum mechanical process, and it produces a molecule and an atom that takes away some of the binding energy. And so the question that we've been asking us for some while now is, what is the quantum state of this rubidium molecule? And there's actually really a lot of quantum states in principle that this molecule could end up in. Yeah, because you have all these degrees of freedom. You have the vibration of the molecule, you have the rotation of the molecule, you have the spin state, you have electronic spins, you have nuclear spins. And if you count it all, there's easily over 100,000 states that in principle would be available. Yeah? So that sounds like a big problem, actually, although you only have three particles. And indeed, even if you knew totally the interactions between the particles, at this point, you cannot fully calculate it. Things have to be approximated. So, there's a certain uncertainty. There's a frontier that we don't understand. So, and that makes it worthwhile, I think, to really ask, so, how can we get a fundamental understanding of what's going on? Are there perhaps any simple rules, any simplifications that we can make? And once we understand this whole process, are there perhaps any control knobs that we can do in order to control this reaction, yeah, on the quantum level. So that's a little bit our motivation. And on the experimental side, yeah, we were a little bit lucky. We found a way a couple years ago how we can measure in detail the product distribution, yeah, of these molecules. Yeah? So we can measure what quantum states these molecules are in and with what probability. So I just want to explain you now on an experimental side, yeah, how we do this. And then actually later, Jose is going to dig more into the three-body theory because that's very complicated. To some extent, we have a double whammy this morning. Yeah? So we get to talk about the same experiments twice. Yeah? So first you get an idea, and then later you understand. Yeah? So here we have a cloud of rubidium atoms, 10 to the 5 atoms or so, and they're at a temperature of a microkelvin. They're held in an optical dipole trap. And then every now and then, 3 of these atoms collide and undergo three-body recombination to form a molecule. And now here in this simplistic plot here, you see, so we have this is now, a two-body potential, and here you have the bound states of these molecules, and there might be some bound states that get populated and other bound states don't. And we want to now measure which ones have been populated. So what we do is we ionize state selectively these molecules. And we do this with REMP, resonance enhanced multi-photon ionization. In our case, we use 2 laser photons. The first photon resonantly excites a level here to an intermediate level. And then it gets ionized. And then we detect this ion essentially with 100% probability. And then by scanning this purple laser over all of these levels that are of interest, we can just see which level was populated and which level wasn't populated. Yeah? And the good news is also that each level typically has its own energy. Just by choosing the frequency here, we can really, go over all of these different levels. And this is now what such a spectrum looks like when we take it. So we scan the purple laser here. This is the laser frequency. You see we scan the laser frequency in that experiment here over like a few gigahertz. And then you see these dips. And every dip that you see here corresponds to a well-defined quantum mechanical state of a molecule. Yeah? And we can resolve essentially rotation, vibration, but also the spin degrees of freedom. And then we can see whenever we have a dip like this one here, we have calculations, and we had also done spectroscopy beforehand, and we can know exactly what level that belongs to. And here, for example, you can see that only the red lines, which correspond to a certain spin state, have been populated. And, well, you might wonder, the spectrum that you saw here, why, these dips that you see here, they correspond to these signals. Why do we see these dips? What does it mean? How does it come about? And I just quickly want to explain. So we carry out our experiment within a linear ion trap, and this ion trap is essentially, in the end, our detector for the ions. So when we detect an ion, we know there was a molecule before in a specific quantum state that we wanted to measure. So, so we have this atomic cloud here, the ultra-cold rubidium atoms in the center. They form a molecule. This molecule gets ionized. It gets trapped in here. But now these ions are, of course, dark. Yeah? We have to kind of detect them. And we have a scheme where we bring in a fresh cloud of atoms. We know the atom number of this cloud. And then we immerse these ions into this cloud. And these ions, they jiggle. And the jiggling, there's this micro motion in the ion trap. they collide with the atoms and they kick one atom out after the next, and after about a second or so, a good fraction of the atoms are be kicked out, and then we know from the amount of atoms that have been kicked out how many ions we had, and that means we know how many molecules we had in that particular level. So now I want to really come to the beam splitter and explain how this works, and what helps me in order to understand what's going on is really that although we have a three-body process, I also think of it in two steps. So we have the two atoms A and B. They will form in the end the molecule. And so in the first step, I look at it as if two atoms come together to close range. And then once they do that, the third atom C comes in. It's perhaps a little bit at a farther distance. It gives them a little bit of a nudge. So now they can relax into a bound state, give off some energy, and the third particle takes away with that energy. So in that sense, I can simplify this complicated three-body process in my mind. And that actually helps us also understand what happens here with the beam splitter. The next thing that is important is that we found experimentally, but also theoretically, when you have the two atoms A and B, they are in the beginning, they are, of course, prepared in a specific spin state. So the quantum number, total spin of atom A is Fa, total quantum number for spin for B is Fb. Then you have the pair, so the sum of the two, that will be given by the quantum number big F, and then you have the projection MF. And all these quantum numbers actually, in the three-body recombination, these spins have a tendency in rubidium to be conserved. So the molecule has the same quantum numbers. And somehow, in principle, atom C could interact also via the spin, but it doesn't do it. A simple explanation is C is a little bit too far away. So now, let's say what this means. Let's say we have here, again, this is the two-atom picture. We have the two atoms. They're prepared in a spin state, which I just call spin up. And it corresponds to the color blue. And so now they collide and come in to a certain distance. Now they get from the third atom the kick. They can relax here. And because the spin is conserved, they will form blue spin up molecular states. There could be a different molecular state. Let's say the red one, I call that spin down. But these guys don't get populated, simply because of the spin conservation. But now, let's say, what happens if we have a Feshbach resonance? So we have now a red level here, in this closed channel, this red channel, and it's very close to the incoming channel here. And then, because of spin exchange interaction, there will be now mixing between the red level and the blue level. So now the scattering level down here, it actually gets a little bit of an admixture of the red level. And that means now that we have some red spin admixed, that we can also produce in the three-body recombination, we can now also produce red molecules, so spin-down molecules. And we can control this admixture, of course, with the help of a magnetic field. By having these two levels closer or farther apart, we can control this admixture. And so then we can also control to what extent we can produce spin-down molecules. So a very simple picture now is that we have this way some bypass valve. So here you have your flux, the reaction flux that come in, comes in, and if you don't do anything, it just goes out this end here. But here you have a lever with a magnetic field, and by turning this, now you can, divert a certain fraction of your reaction flux into another channel, another spin channel. Yeah? Now, this is very mechanical and easy to understand. Of course, in the end, it should really be a coherent process. Yeah? So, that's what I show like this. Yeah? So we have a tunable, coherent beam splitter here. And this is what it looks like now in terms of levels. Yeah, here you have the magnetic field in Gauss. These are the binding energy of the molecules that we produce. This is binding energy 0, and up here, at 0 energy, you have the incoming state, which we just call spin up. And so wherever you see a blue line, these are spin up molecules. The red lines, they correspond to spin down molecules. And here in green, you still have another spin state. Yeah? And here you see now, at about 55 Gauss, there's a crossing here of this red level with our incoming state. So this is now, where the Feshbach resonance sits. Yeah, so this is what I showed you before. This leads to this mixing of these two guys here. So now, if I, let's say, do this recombination experiment at 50 Gauss or so, I would be here. The Feshbach resonance doesn't play a role, and I would only populate spin-up molecules. But if I do the experiment at 150 Gauss, here I have the spin mixing. I would then also expect, beside producing blue molecules, I would also expect to produce red molecules. And in fact, now we're going to investigate this. And from all these levels, we're just going to look at 3 levels and then see, how much signal we see in those. And this is now in this plot. Yeah? So you have here scans where we scan our laser and we look for molecular signal. Whenever you see a dip, that's a molecular signal. And here in green, you have the magnetic field. So here we start essentially at 0 magnetic field, and then we go up to 150, even 160 Gauss. So the Feshbach resonance is around here. So what you see now at low magnetic fields, and we're far away from the Feshbach resonance, you only have this one peak, and that's actually corresponds to our spin-up molecule that we observe, just because of the spin conservation. But now as we go to 100 or 120 Gauss, you all of a sudden see there are little signals coming up here, and they grow until we get to this Feshbach resonance at 155. And actually at that point, they are just as strong as the spin-up state. So here, you can see now, so somehow we have a control over producing these final states. And indeed, so these guys here, these are spin-up molecules, and these guys, they are spin-down molecules. And I just want to show you, so the spin-up molecule is this one, has a rotational angular momentum of 4, and the 2 spin-down molecules are these ones here. It doesn't really matter. We could have also picked other ones. And this is now in a more quantitative way what we have observed. Here you have, again, the magnetic field. Here you have the signal strength in blue for our spin-up state. So even at 0, low magnetic fields, it's very strong and it stays strong. But then the spin-down ones, they first were below the detection limit, and then they grow over essentially 2 orders of magnitude until they have the same signal strength as our spin-up state. Here's, by the way, the Feshbach resonance, and here we have an Efimov resonance. You see there's a little bit of a local maximum, but actually the Efimov resonance is not a good resonance for this control that I was talking about. You really need the Feshbach resonance, because the Feshbach resonance does the spin mixing, the Efimov doesn't. Now, what is also striking is that just above the Feshbach resonance, all the production signals of the molecule go down again by orders of magnitude very quickly. And the reason for this is simply that here this is the scattering length. The Feshbach resonance has a zero crossing here at 160 Gauss. So when the scattering length vanishes, then also the recombination signals normally are very small. So that's how this is explained. So in the end, yeah, this is how this Feshbach beam splitter works. Yeah, you can create with the help of a magnetic field, the output of your reaction, you can create some other spin states. So now I want to get to the second kind of beam splitter based on the avoided crossing. But I'm going to use the same picture, and I just want to quickly repeat again what we have just learned. So we have here this incoming channel, and you had this Feshbach level here. The mixing of the two led to the fact that now the scattering state had also some spin-down component, and that meant that you could also produce spin-down molecules. Now we're going to have a case where we don't have the Feshbach resonance. Actually, before we've been working with rubidium-85. There's a nice and broad Feshbach resonance. We use that. Now we're going to work with rubidium-87. There's no Feshbach resonance that can be used for this conveniently. And so we have more like this state here. So our incoming spin-up state, it will just, stay blue. Yeah? And now we're going to play the same or similar trick down here. We're going to have mixing of molecular levels. Yeah? So we tune two of these molecular levels close to each other. And then, because of spin exchange interaction, they will mix. And so if you now have the red level here, for example, normally it wouldn't be populated, but because now due to the mixing, it gets a little bit of a blue admixture. And so now you can populate it for that reason. This is the idea. And here you see this again in terms of bound states as a function of the magnetic field. You see here, this is the binding energy of these molecules. This zero energy, this is our incoming state up here, our scattering state of the two atoms. And then here you have another spin up state in blue. But there's an avoided crossing now with a spin down channel here. And where they cross, of course, the colors mix. So you will have something that is like magenta or purple, yeah? So this is what I indicate here. And so now let's say we go to different magnetic fields and we have our three-body recombination. If you're far away from this crossing, then the incoming blue state will only produce a spin-up blue molecular state here, and also on that side. But if you are, at a magnetic field where you have this crossing, now you can populate both states, yeah, the upper one and the lower one. Yeah. So let's look what the experiments say. We kind of zoom into this here. The first thing that we did was, of course, a little bit of spectroscopy. So this is this avoided crossing. Yeah, magnetic field, binding energy at 100 Gauss or so. This is where we have this crossing. So now we have an upper branch and we have a lower branch. Let's see how we can populate these branches. So we do this now at different magnetic fields here, for example, close to 0, 80, 120, and 140. And you see when we do this at like 4 Gauss or so, here we get a big signal, yeah. So we populate this level very strongly. Here we have a negligible signal, very small. Now we do the same thing at a higher magnetic field, 80 Gauss or 100, and you see that this signal that was essentially 0 here now really has grown. And at the same time, this guy, as you go all the way to 150, it goes down. So you can see by now choosing different magnetic fields, you can populate one or the other level, yeah? And to make sure that the overall flux that we produced was kind of constant, we have also a reference level. This is a third level I haven't talked about before. So this one is a level that is just not crossing any other level. And so the signal that we get here is pretty constant. Yeah? So with this, I do the same thing now, look at it a little bit more in a quantitative way as a function of the magnetic field. We look at the production signals of the lower level and the upper level. You see at low magnetic fields, all the reaction flux goes into the lower level and essentially none into the upper level. Now, as we get close to this magnetic field of 100 Gauss, 120 Gauss or so, this one grows, this one goes down until at the avoided crossing they have about the same flux, and then you can invert it even. And this can be compared now with our simple idea, that the spin content, the spin up content of the upper and the lower level plays the important role. So the lower level, the spin content, the spin up content of the lower level is plotted here. Yeah, so at low magnetic fields, it was essentially 100% spin up. And then, it goes to like 50 at the avoided crossing, and then it goes even lower. And the spin, the upper branch, it started out with a very low spin up content, and then it increased. And you can see here, that these patterns actually very nicely follow that. Yeah, so we have a very simple interpretation of what's going on, and this will also help us then in the future perhaps to do some interesting stuff. You can, by the way, also compare to a full three-body calculation. So this is now what Jingloon and José have been carrying out. So this is now a calculation. You see qualitatively it's the same thing. By the way, the crossing is a little bit shifted, but that has to do that they have to do something to the model. They have to simplify these potential energy curves. José can explain it. But I would say we have a nice qualitative agreement and to a good part also quantitative. It's not perfect, but that's also because this problem is really complicated. In the end, it's a three-body problem, not just a two-body system. So now that I've introduced you the two beam splitters, I want to take a step back and kind of like look at the whole system now from a distance and say, okay, so what in general, what have we done? Yeah, so we have these three atoms. They come together. They want to form a molecule. As they get together, there is a regime that you could call a collision complex that they form, where they all interact. Here, up here, this arrow is kind of a reaction coordinate, some time. Yeah? And at some point, these particles will separate again, but then here you have the molecules, you have many channels that you can end up in. And that I call the exit zone, and here this is called the entry zone. And our Feschbach beam splitter, that was kind of something that happened here at the entry zone. Yeah? So you start out with, let's say, a blue system, and if you don't do anything, it stays blue, and it can produce all different kinds of molecules, but they're all blue. Now you turn on the beam splitter, then you can, divert a certain fraction into red states they can propagate through and produce corresponding molecules. Yeah, and we've just looked at a couple of those. And now for the avoided crossing beam splitter, so this happens at the exit zone, where the molecules are essentially already there. And so here we enter just with the blue, and then one particular reaction path hits this beam splitter here, and then depending on what magnetic field we have, we create this magenta or this purple molecule, and we can control how much goes in there or goes in there. Now you could think about what happens if we have the two beam splitters combined, you know. So we have one in the entry zone and you have one in the exit zone. And you could say, okay, let's say, so we have this path here where the blue just goes right to this beam splitter, creates the two. But you could also think, okay, perhaps now here we have a certain flux of the red path, and perhaps some part of it also hits the same beam splitter again, and then, you know, can also produce this purple or the magenta molecule. Now you see that here we have now a closed system, yeah, a loop, and there could be interference. Yeah? So that's something that we are excited to look into for the future, yeah, to see to what extent one could see some interference in this reaction system. Now, with this, I want to conclude. So I talked about three-body recombination. Three rubidium atoms come together, and we have gained some control in the reaction. We can divert, you know, what kind of molecule they end up in. And for this, we had two different schemes for beam splitters, the Feshbach resonance and the avoided crossing of molecular levels. Both ideas, both beam splitters kind of are based on mixing spin channels, yeah, within this collision complex. And this way, we could really redirect a sizable fraction of the reaction flux from one channel to another channel. And now, looking at the whole system, we see that one of the beam splitters kind of in the entrance zone, the other one in the exit zone, and perhaps in the future, one can use that for some interferometric control. Thanks very much.
Thank you very much. Questions? Yeah.
Very beautiful measurements of the spin polarization and mapping of the avoided crossings with the magnetic field. But my question is more sort of bird's eye view. Are you trying to say that with this, both these Feshbach spectroscopy or interferometry, you're actually isolating the three-body recombination states? Because if I want to have a Feshbach, the normal Feshbach resonances, I don't need a third body, right? I have the magnetic field.
Oh, yeah, so how people used to produce molecules very efficiently, actually, is by ramping, yeah, the magnetic field over a Feshbach resonance. And that works, and that's a great control. Here, we are just really looking at three-body recombination. So the focus is not so much producing molecules in a particular state, because there are ways, but it's really also understanding the three-body recombination and getting, kind of like working with that, yeah? Although it's perhaps not the most elegant way of producing a particular quantum state, but it's just, fundamental research in that sense, yeah?
Yeah, the last idea is very, very interesting. That seems to require you can find a magnetic field such that you have Feshbach resonance as well as the void level crossing at the same field.
Yeah, so this is, of course, you have to be lucky, or it's also convoluted. It would be better to have a scheme where you can control the two beam splitters independently. Yeah, but you haven't asked your question yet. Yeah.
Right, so I guess one possibility is to use some kind of optical induced Feshbach resonance, and then you go to magnetic.
I like that idea, and I've been, thinking about this, and you have actually found a beautiful scheme to do this. Yeah, so we could be thinking about going this way. Yeah.
Yeah. So with your two bosons, you form a molecule, and there's an electron missing. Is it that it's just a fermion then, your molecule, right?
No. So we have neutral particles here, and the two all atoms are rubidium, so they are all bosonic, and so in the end we also will end up with a bosonic molecule.
Okay, but so this is not. Then I got this wrong. This is not at the end when you did your collision a rubidium 2+.
So yeah, so this is when we kill the molecule. Yeah, so it's a neutral molecule, and now we want to detect it, and we kill it by ripping off one electron. Yeah, then it's easy to detect. Yeah.
Just to follow up on Ching Sen's question, which was a very good question, and the optical idea is very interesting. A number of years ago, you had used microwave or RF control to control avoided crossings in rubidium, and I'm just wondering if you could use a microwave or RF active control field to put a crossing wherever you wanted it.
And I want you guys to calculate that.
Yeah, I mean, this is so beautiful, the level of control and detection. Now that you have, I'm curious whether you've looked where there would be an expected four-body resonance.
Yeah.
You have looked.
No, not actively. Yeah, but still, I would like to talk to you about it. Yeah.
Yeah.
I was wondering if there's any estimate on the lifetime of the three-body complex, extension of that, whether there's a possibility to directly write the three-body complex in your system.
So repeat again. Yeah. So you
So
have the two-body state that or the three-body state. You were wondering about the lifetime.
Yeah, like how long did it stick together
of that?
before?
Yeah, that's a very interesting question. Of course, it depends a little bit on the regime where we work in. I would say once you get close to the Feshbach resonance, you know that within the Feshbach resonance there is a certain lifetime of the two-body bound state. If we're farther away, now that wouldn't play such a big role, and then probably also, I'm not even sure. Would you have a number for the lifetime? But it's certainly just like one of these direct processes. Yeah. So lifetimes do appear in these resonances. And what was the second part of your question?
I guess to kind of follow up on the first part, I'm kind of thinking about this from an RKM perspective. Right? You have this three-body complex. It's a pretty heavy atom, so you have pretty high density of state, and you only have one or two active channels out of this complex. Right? So that's a recipe for a very long complex lifetime. So I was wondering.
Yeah, and I don't know so much about. I think that José perhaps can give a better answer than me.
Are you referring to some of this steep?
Yeah, exactly. How long does it stick?
It's not a very high dense energy there. I mean, there isn't many triatomic states above the continuum. Because those are atoms with molecules, probably would get a much denser energy spectrum. So it's rare to stumble in one of these complexes.
Right.
So there's no steep collisions.
Okay. All right. That answers my question.
So the resonance, the film of resonance that you show here is the film of resonance at negative scattering.
The Feshbach resonance.
The film of resonance. You show here the green, the film of resonance here.
Yeah.
So it's the film of resonance for the negative scattering, right? Is
Yeah.
that correct? So, and there is also
So
probably on the positive scattering should be another.
So Efimov resonance that we observe here is where you don't have two-body bound states. So it
Yes.
corresponds to the positive scattering length side.
Oh, that's the positive
Yeah.
scattering side?
No? Am I wrong?
That's the negative side.
That's the negative side.
Okay, sorry.
So then, on the positive side, you should get also, which is different because you have a bound state right there. So it can behave differently then. So from
I
that
guess on
point
the
of
positive
view.
side, we never explore much, right? At least experimentally. Have you ever seen the Feshbach dimer, for instance?
No, as you see, all the signals go very quickly. downhill, yeah, and we don't.
So
Yeah.
the atom dimer, the film of resonance was never sort of, well, because this is the continuous, yeah, start for the continuous. It should not be observed. Okay,
That
sorry.
would be interesting to look to the
Yeah,
Feshbach
like you should prepare the atom dimer mixture already and then start to look for that. And that maybe the resonance also can give you some sort of control. Because you start with the timer already a mixture of states.
Okay, perhaps we can also
Yeah.
discuss it a little bit more in detail later.
No? Any further questions? That's not the case. Thank you once again.
Yeah, thanks.